Hello, testing. All right, so today is the last day. We started with the earliest time in the semester and end with the latest time in the semester. Okay. Uh, and as last time I told you guys, so your I have some special feeling for your class because your class is my first MAT class. But I guess I have a strong feeling that we might not meet each other again in future unless you choose to do a pure maths. Yeah. Okay. Yeah. So but that's fine. But I still hope that you will get better. Okay. Maybe if you don't like me, that's fine. Yeah. Sure. That's fine. That's fine. Because we have different path in our life, right? Maybe we don't intersect anymore again, right? That's fine. But I still hope that you can do well in your own path. Okay, I hope you will do well in your own path. If what I say makes sense to you, benefit you, please keep it. Okay. If not, just forget about it. Okay. Uh, maybe one day you don't remember me. I don't remember you. But if you do remember me, maybe you can greet me. Yeah. If I forgot your name, please tell me your name. Yeah. Seriously, because I always forgot. But I remember your face. Okay. I can remember face, but name sometimes I forgot. Okay. Yeah. Okay. Because I already have like first semester students ask me, you remember me or not? You look very familiar, but I don't know your name. First semester I got 200 students, I need to mark 200. Not remember it. Well, okay. So since this is the last day, I already covered what have to be in the exam. So I'll continue to speak about what's next. Okay, after the abstract algebra. Okay, what's the next thing? If you want to continue, okay, doing pure maths, what's thing you expect? Okay, what will you expect? Okay, in pure maths, there are few direction you can go from pure maths. Point of view. Last time I already told you about the algebraic geometry, right? So you can see the ring homomorphism as a map, as a parametrized equation, parametric equation, right? Remember the example I showed you? X tends to t, y tends to t squared, z tends to t cubed. The example you have in your assignment. Okay, you can see it as a space curve. Okay, in that sense. Okay, this is about last lecture. And then next lecture, hopefully I'll talk a little bit about representation theory, and then hopefully Galois theory. So where's Y? Where's the? Yeah, those two are the ones that mentioned last time. Yeah, maybe I can show you some using the example that we have in my assignment. Okay, so before that, let's go into maximal ideal. I guess you don't need to do notes, right? You just listen what I say. Listen to what I say. Okay, I'll talk about maximal ideal first. So what's the maximal ideal here? Okay, so let's start with the motivation. So similarly, we will consider a surjective homomorphism. Okay, homomorphism from a ring to field F. Okay, what it see. So let's write like this. So E from ring to a field F. So remember what's the field is? What's the difference between field and ring? Okay, field is just all the non-zero elements are invertible. Okay, and this gives one characterization of ideal in F. So F only contains exactly two ideal. Okay, there's exactly two ideal inside here. One of them is the zero ideal. The other one is the unit ideal. Okay, they are exactly, so let me put the point here. So they are exactly two ideals in a field. Okay, so this is surjective. Field is a ring. So we can use correspondence theorem here. Okay, we can use correspondence theorem here. So what does correspondence theorem tells you? There's a bijection between the ideal in the core domain with the ideal containing kernel in your domain. Okay, so in this case here, there are how many ideals that contain kernel now? Should be two. Okay, should be two because there are only two ideals on the core domain. So there must be two ideals that contain the kernel. So what are the two? One of them is the kernel. The other one is the whole ring. Okay, so this is the bijective correspondence. Okay, by correspondence theorem. Okay. Okay. Yeah. So your field has only two ideal. Then there's only two ideal that contain the kernel inside your ring. Okay, so these are the two ideal. So in this case here, so in this case, we will call I the okay, I is a maximum. Okay, we'll call I an maximum ideal. Because I is the thing that contains the kernel, and then any other thing that contains kernel must be the whole ring. Okay, we call I is a maximum ideal. So in general, what is I here? So other than the ideal that contain kernel, it is either I or the ring. Okay, so let me make this definition. Okay, so what is a maximum ideal? So a maximum ideal M, okay, of a ring R is an ideal. Okay, is an ideal that isn't equal to R. Okay, it is an ideal that is not equal to R, and that isn't contained in any ideal other than M and R. Okay, so what does this mean? Okay, so in other words, okay, in other words, if an ideal I contains M, okay, then I equals to M or I equals to R. Okay, so let's look at one example. Okay, one example here. For example, the ideal generated by 3 in Z. Okay, the ideal generated by 3 in Z. I claim that you cannot have a larger ideal that contains 3, which is proper in Z. Okay, you cannot have a larger ideal that contains 3, which is proper in Z. So this is maximal ideal. So let me give you a non-example, maybe easier for you to see. So I'll say that the ideal generated by 6 is not maximal. Okay, because why? Because I can find a proper integral, a proper ideal that contain the ideal generated by 6 in Z. Okay. So this ideal generated by 6 is not maximum, but 3 is maximum. Okay, and then note that 3 is prime actually. Okay, no. Yeah. So I can actually make a proposition here now. So what's the proposition? Proposition. The maximal ideal of the ring Z, okay, which is we call the integers, are the principal ideal generated by prime integer. Okay. Okay. So this is true. So you can see we can first prove that the ideal generated by a prime P is maximum, where P is prime, where P prime. Okay. How to prove this is maximum? Suppose it is not, right? Suppose for contrary, suppose for the sake of contradiction. Okay. The ideal generated by P is contained in some other ideal generated by M. Okay. Why? Right? Which is the proper subset of Z. Why can we do this? Huh? Because since what? Since Z is a principal ideal domain. So what does the principal ideal domain means? It is an integral domain where all the ideals are principal. Okay, because every ideal in Z is generated by one number. Okay, so we can say that it contains in other proper ideal that is generated by one element, for example, M. Okay, so this means what? This means what? The ideal generated by P is contained in ideal generated by M, meaning what? P is a multiple of M. Okay, so this means what? This means P is in the ideal generated by M. Okay, that is P equals to M times maybe K or some K in Z. But what? P is a prime. P is a prime. Okay, P is a prime means what? P is divisible by what? But P equals to what? Equals either P times 1 or 1 times P. That's the only thing you can happen. Okay, P equals to P times 1 or 1 times P. Okay, this means what? Either M is P, K is 1, or M is 1, K is P. Right? If M is P, then it is just the ideal generated by P itself. Okay. If M is 1, meaning what? It is the whole ring. Okay. So this says that the ideal of generated by M must be the ideal of P or the whole ring. Okay. Contradicting that it is a the ideal generated by M is proper. Okay. Yeah. Okay. Huh? Thank you. Okay. Yeah. Okay. So I proved that the ideal generated by M is proper. The ideal generated by prime number is proper. How about the other number? Okay. All the other numbers are product of prime. Okay. So next, we have to show that ideals like Mn, okay, are not maximal. Right. So these are not maximal. Why? Since we can find a proper ideal that contain the ideal generated by Mn. What's the proper ideal that contains ideal generated by Mn? M. I can pick M. Ideal generated by M. Or ideal generated by N also can. Okay. This is a proper ideal. Okay. That contains the ideal generated by Mn. Since this is true, we have the ideal generated by Mn is not maximal. Okay. Okay. Yeah. Okay. So what do we have now? We know quite a lot of things about the quite a lot of things about the ring of integers. Okay, we know that every subgroup is cyclic for integer. Every ideal in the integer is principal. Okay, now we know that all these principal ideals are maximal. Yeah, so integer is kind of quite interesting. We have a lot of good property now. Let's see what we can do with these. Maximal ideal. Okay, so let's see what we can do with this maximal ideal. So suppose we have a surjective ring. Let's be a surjective ring homomorphism with kernel I. Okay, is a ring homomorphism surjective. I have kernel I. Then the image R prime, okay, is a field. Okay, if and only if I is a maximal ideal. Okay. So we can know that this image here, whether it's a field or not, just by knowing what's the kernel of this map. If this kernel of this map is a maximal ideal, then I know that the image is a field. Okay, just by telling me what's the surjective ring homomorphism, and then tell me what's the kernel, and then I will know that R prime, the image, must be a field. Okay, we will prove this. B is what? An ideal, okay, an ideal of a ring R is maximal, okay, if and only if I take the quotient of R by the ideal is a field. Can you see that? Part B follows from part A? If you have a surjective ring homomorphism, okay, you know the kernel, you want to consider the quotient ring. What is that? You can use the first isomorphism theorem. Okay. First isomorphism theorem tells you that R mod I is isomorphic to the image R prime, which is a field by part A. Okay, so B follows from part A using first isomorphism theorem. Okay, So B is more practical in practice, okay? In real practice, okay? In real life, it's more practical. I have a ring. I just quotient out by a maximal ideal. I get a field. So just now you have an example. What's the maximal ideal in Z? Or the ideal generated by prime. So Z mod prime ideal generated by prime. What do you get? Z mod PZ, which is the field of mod P. Okay, so there are P prime elements inside there. Fair enough, right? Z mod PZ. Okay, yeah. So in general, how we find Z mod PZ? I mean, how we generalize Z mod PZ? We take a ring, quotient by a maximal ideal. I get a field. Okay. Yeah. Why field is interesting than the ring? Because in field, all the non-zero element I can invert. Okay, in ring we might not. Okay, C. What is C? C, the zero ideal of a ring R is maximal if and only if R is a field. Okay. The zero ideal of a ring is maximal if only if R is a field. Because all ideal contains zero, right? Every ideal contains zero. Okay. If zero ideals is maximum, meaning what? Only zero ideal contains zero, or the whole ring contains the zero. Okay. Then this is the only two choices you have. So this ring has exactly two ideal. So it is a field. But Jingsen pay more attention than the others. Be prepared next semester. Okay. I don't know. Okay. Continue. Okay. So let's prove the first one. Okay, let's prove the first one. The other two will follow easily. Okay, let's prove the first one. Direction. So what's direction? So let's go from left to right. So suppose the image is the codomain is a field. Okay, we want to show that the ideal is maximum. Okay, the kernel is maximum. Okay, let's show this. So how to show this? Okay, how to show an ideal is maximum? You need to show that every ideal that contains I is just I or the whole ring. Just these two. Or just these two ideals. Okay. So how do you do this? Okay, how to do this? What's the information you have? You know that R prime is a field. What's about field? What's about field? What's the ideal in field? What are the ideals in field? Yes, so R prime has exactly two ideals. Okay, so what are them? One of them is zero. The other is the unit ideal. Okay, so we can use correspondence theorems again. Okay, because we have surjective homomorphism. Okay, so correspondence theorem will come in handy. So by correspondence theorem, how can I find the ideal that bijects to these two ideals? I can just take the inverse image. Okay, I can just take the inverse image. This is the map that how we find the bijection, okay, between the two ideals. Okay, we can look at the inverse image of zero and the inverse image of the other ideal, which is the unit ideal. Okay, so what's the inverse image of zero? What is this? Yes, this is the kernel. Okay, so this is the kernel, which is I in our case here. Okay, this is the kernel of the map V, which is I in our case. And What is the inverse image of R prime? My map is surjective. So it's the whole R. Okay, it's whole R. Hey, where is Syed, by the way? Sorry? Balik Kampong. Wow. Early holiday. Okay. So by correspondence theorem, these two are the only ideals that contain I. So this is the only two that contains I. Oh, maximal ideal. What's the definition of maximal ideal? One ideal is maximal. Either any ideal that contains I is either I or the whole ring. So this correspondence tells you that there's only these two that contains I. Okay. So by definition, it says that I is maximum. Okay. Yeah. Okay. Yeah. Because how to be maximal? Remember the example in Z. Ideal generated by 6 is not maximum. Why? Because it contains in other proper ideal, okay, which is not Z. 3 is maximum because you cannot find proper ideal that contain 3. If you want to go further, you need to go to the whole ring. Either 3, either the ideal generated by 3 or the whole ring. Okay. Okay, the other direction. Okay, the other direction is similar. Suppose I is maximum. Okay, suppose I is maximum. We want to show that R prime is a field. Okay, so I is maximum means what? The only ideal that contains I is either I or the whole ring. Okay, the only ideals containing I's are I or the whole ring. And I claim that we're done. Why are we done? Again, we use correspondence theorem. Correspondence theorem is a bijective correspondence. So we don't just can go back from codomain to domain. We also can go from domain to codomain. We already know that only two ideals that contains kernel in the domain. So if I map across using correspondence theorem, there's only two ideals inside my codomain. Okay. So by correspondence theorem, there are only two ideals in R prime that correspond to I and R. Okay. So your codomain only have two rings or two ideals. So meaning your codomain is a field. Okay. Since R prime has exactly two ideals, prime is a field. Okay. So this is how we get field. Okay. How we get field. We take a ring, I mod out a maximal ideal. I get it. Yeah. So last time I claimed that there's a lot of similarity between integer and polynomial ring, right? Okay. So what's the thing that play a role of prime inside polynomial ring? Okay. So we'll define this this object here. A polynomial ring. A polynomial with coefficients in a field. Okay, so we just consider polynomial ring over field. Polynomial is called irreducible. Okay, irreducible. I believe some of you seen it in the ALA, is it? Have you guys seen this in ALA or not? It's irreducible polynomial. Okay, it's called irreducible if it is not a constant. Okay, and if it is not the product of two polynomials. Okay, of course, these two I cannot have both of them. One of them to be the constant. Okay. So let me give you example here. Okay, so what's irreducible polynomial mean? So for example, s squared plus 1, right? S squared plus 1 is irreducible in, let's say, Qx. Q is a field. But s squared plus 1 is reducible if I change my field. Okay, because if I change my field to complex, I have a root x. I have a root x plus I times x minus I. Okay. Okay, no. Okay, so you have an idea of irreducible polynomial here. So similarly, we can do this proposition using exactly the same way in integer. Let f be a field. Okay. F be a field. The maximal ideals of fx are the what are these maximal ideal? Are the principal ideal, right? So fx is a principal ideal domain. And then what are the maximal ideal? These are the ideals that generated by the monic irreducible polynomials. Okay. So this proof is similar to the Z case. Okay. Similar to Z case, where the prime, where the yeah, I should say where the irreducible polynomial plays the role of primes in Z. Okay. So actually you have seen this example already, right? So I have a irreducible polynomial s squared plus 1 in zx, right? Okay. So what is zx portioned out by this maximal ideal? Hey, sorry. We need a field, right? So let's go to a field here. So let's go to rational here. Okay. So what is this ring here? Huh? This ring is what? It's just Q adjoin I. Okay, it's just Q adjoin I. And then the claim here, this is a field. Okay, is this a field or not? Is everything here invertible or not? Okay. Rational numbers are invertible or not? Invertible, right? So now the question is I invertible or not? Does I have an inverse? What's the inverse of I here? Minus I. Okay, it's minus I. Okay, so actually this is a field. Okay, so this is a field. This is a field. Okay, because Q is invertible. Right. Q, okay, not Q, but Q slash up 0 is invertible. And I is invertible as well. with inverse minus sign. Okay, yeah. So you don't just get a ring, actually you get a field. Okay, yeah. Okay. So now I think it's now the time to go into Galois theory a bit. So how do we see Galois theory here? So what's the example in your assignment? Let me see. Assignment. Okay, so you have a map sending x to square root 2 plus square root 3, right? Okay, you have this map in your assignment. So let's go a little bit into maybe, I think AA2, Galois theory. Okay, so what's this? So let's fix this ring here. So let's fix it as a qx to q of q. Let me see. Okay, so let me just put q adjoin square root 2 plus square root 3. And this. Okay, between two ring. Okay, ring. Make sense? Okay. So what's the polynomial you found? What's the kernel you found in your assignment? What's the kernel of this map here? Have you proved it? What's the kernel of this map? Turn off it. X4 minus 10 x squared plus 1. Okay? So this is the smallest degree polynomial that have the root square root 2 plus square root 3. Okay? So actually this function, this polynomial is, so let me write here. So this function here, so let me call it P. So P is irreducible. Is irreducible in QX. Okay. So what can I do? In this case here, what is this? Wait, let me see. If I leave out something, here. Okay, so this is irreducible, meaning what? This kernel is actually a. So just now we proved what? We proved what? What have we proven? The maximal ideal of a polynomial ring over a field are the principal ideal generated by monic irreducible polynomial. So here, this polynomial here is irreducible, and it is monic. And this is over a field, a polynomial ring over a field. So kernel phi is actually maximal. Okay, so I can take QX. I can take QX. I can take QX. Quotient out by the kernel. Okay, ideal generated by x to the power 4 minus x times x squared plus 1. Okay, what is this? So you learn that if you have this is isomorphic to q adjoin the root of the polynomial that you quotient by. So what's this root here? Square root 2 plus square root 3. But just now I tell you that if you quotient out by a maximal ideal, you get a field. Okay, so you are getting a field, not just a ring. So I changed the bracket to round bracket, denote the field. Okay, so here actually is a field. Okay, so you get a field here. You get a field actually. If you play around with this field, right? Okay, let's play around with it. Okay. So how to play around with it? I can try and square this guy. Can I square it? Because I'm in a ring, right? So I can square element in ring. So I squared it, what do I get? plus 3, which is 5 plus 2 square root 6, right? So this means what? This means that actually square root 6 is inside my field. Correct. Okay, square root 6 is inside my field. Okay, I can play more games. I can take square root 6 multiplies square root 2 plus square root 3. What do I get? I take two ring elements, multiply together. Okay, my ring is closed. So I get square root 12 plus square root 18. What is this 2? Square root 3 plus 3 square root 2. This is significant. Yeah, why is it significant here? I have 2 square root 3 plus 3 square root 2. On the other hand, I have square root 2 plus square root 3. Okay, I can multiply 2 to this root here. And then I take the difference. What have I produced? I've produced a square root. Meaning what? Meaning square root 2 is inside the ring of Q adjoint square root 2 plus square root 3. If I found square root 2, I can also find square root 3. So this means what? This means what? This Q adjoining one element here is actually equals to Q adjoint square root 2 comma square root 3. You actually adjoin two things into this ring just by adjoining one element. Okay. Okay, we are not done yet. We are not done yet. Okay. Your brain need to be big if you want to study pure maths. Too small cannot teach. Okay. You cannot accept, not that I cannot teach. Okay. So what's Galois theory here? So Galois theory, so let me define for you. So what's Galois theory here? So we say that this is Gal of this thing is called a Galois group. Okay, is a Galois group whose elements are automorphism. So what is automorphism? Okay, I put this in your exam. What are automorphism? So it's a isomorphism between the same group. Okay. So are the automorphism of the ring adjoint square root 2 comma square root 3 fixing the coefficient Q here. Okay, we fix Q, but we play around with the roots. Okay, we play around with the roots. So how can we play around with it? How can we play around with it? Okay, there are not much choice. Okay, there are not much choice here. Okay, there are not much choice. What can we do? So let's define an automorphism. Define automorphism. Let's call it phi1. That's mean I got few of them later coming up. Square root 2, square root 3. Back to itself. Okay, what can we define here? One easy one you can do is you just send square root 2 back to square root 2, square root 3 back to square root 3. The identity. Okay. What else can you do? Okay. If you try some possibility, you will get that. You can do okay, let's don't write down the domain and codomain anymore. Just tells you where should the generator goes. Okay, I can send square root 2 to negative square root 2. Okay, and I can send square root 3 to negative, sorry, just to square root 3. Similarly, I can define phi3 I can send square root 2 to square root 2, and I send square root 3 to negative square root 3. Okay, I can do this. Okay, if you check out all the possibility of fixing Q, then these are the possibility you will get. Okay, and then they form a group. They form a group. Okay, so you can compose, for example, phi2 and phi3 together. What do you get? So I compose in the other way. If you compose these two, what do you get? Okay, first you send square root 2 to negative square root 2. You send square root 3 to square root 3. And then you send negative square root 2 to negative square root 2 again under phi 3. And you send square root 3 to negative square root 3. So what's this map here? This is actually equals to the negative of phi 1. Okay, so it form a group. Okay, form a group. And what group is this? So what group is this? So this two generator here, if you go and get the multiplicative table out, you can see that this group is actually, let me write. Z2 cross Z2. Okay. You can see that phi2 and phi3 has order 2. Yeah. And then they commute. Okay. They have order 2 and then they commute. And then these two are the generator of the group. Okay. But what about this Galois group? What about this Galois group? Why we care about this? Why do we care about this group here? Why do we care? Yeah, sorry. Yes. Yes, group of map. Yes. Group of automorphism, not just random map. It must be invertible, yeah, in particular, because we want to form a group. Okay. Yeah. Yeah. Okay. Okay. And so what about this group here? Okay, what about this group? So the claim is theorem, there is a bijective correspondent between the normal subgroups of the Galois group, Galois group of QX, just of Q, and the what we call the intermediate field extension of Q adjoint square root 2 comma square root 3, okay, over Q. So what do I mean by intermediate extension here? So note that what we have did just now, we adjoin what we have did just now. We adjoin a root to this Q. What is that? Square root 2 plus square root 3. But I show you that this is actually equals to the Q adjoint root 2 and root 3. Okay, so what can we do? So we can actually first adjoin Q with root 2 first, or we adjoin Q with root 3 first, and then I adjoin the other root like this. Okay, I can do this kind of extension. Okay, for example, first extension here, what do? I kill by the polynomial s squared minus 2. Yeah, s squared minus 2. Okay, I kill by the polynomial s squared minus 2. So let me write down for you. Q by the polynomial s squared minus 2. Okay. How about the other side? The polynomial Q by the polynomial s squared minus 2. Like this. Okay. And then I Q again. Okay. Yeah. Okay. Then if you want to go further, maybe I can consider this ring Q adjoint square root 2, and then the polynomial ring over this and then I Q by s squared minus 3. And then the other way is similar. So the claim is I have subgroup of a Galois group that correspond to all this guy. Again, all this guy here. So the Galois group. So I have a Galois group Z2 cross Z2 here. Z2 here. So the one easy subgroup is, so let me put it here. Okay, so this is on the other side. So wait, let me call this. Let me make it smaller a bit. Size here. The claim is one side I have groups, okay, which is the Galois groups. And then the other side, I have field extension. Okay. So what are normal subgroup of Z2 cross Z2? Group of order 4. How many subgroup there? How many subgroup? How many normal subgroup? Since this group is abelian, right? So all the subgroups are normal. Okay. So what's this element? What's this group? I think the first day I teach you multiplication table is Z2 cross Z2. So what are the elements here? 0, 0, 1, 0, 0, 1, 1, 1. Okay. Yeah, what are the subgroup here? What are the subgroup here? I can form a trivial subgroup. Right, trivial subgroup. Yeah, trivial subgroup is what Sun Ling said last time, trivial subgroup. Always you have a trivial subgroup. Yeah. And then what else? What else? What other group you can form? All the subgroup have to divide the order of the group. So the order of the group is 4 here. So what number divide 4? 2. So you need to find subgroup with order 2. Is what? 0, 0, 1, 0, and 0, 0, 0, 1. Right. Okay, so these are the subgroup. Not just subgroup, they are the normal subgroup because our group is abelian. Okay, I try to put everything together. A lot of things have to work, otherwise nothing will work. Okay, so these two elements group form Z mod 2Z. Okay, so exactly these two field extension correspond to the Z mod 2Z normal subgroup. And then the last one is identity. So what's the Z mod 2Z? So meaning what? Meaning what? The Galois group of Q adjoint square root 2 is 2. So meaning what? Meaning there are only 2 automorphisms here. Okay, so here means what? So let me put it here. So what does this 2 correspond to? So the Galois group of Q square root 2 quotient, not quotient, fixing Q over Q is a Z mod 2Z. So there are only 2 elements here. One is identity, one is phi. What is phi I here? I just sense square root 2 to minus square root 2. Okay, I do twice, I get the identity back. Square root 2 to negative square root 2, And then negative square root 2 go to negative square root 2. So negative, negative become positive. V1 square is identity. Okay. Yeah. And then this this link back to our story that an is not is what? It's simple when n is greater than 5. Greater or equal to 5. An. Remember last time we have an example that example the alternating group an, okay, is simple for n greater or equal to 5. So what does simple mean? It doesn't have a proper subgroup. It doesn't have proper subgroup. Okay. So if your Galois group is happen to be A5, right? Happen to be A5, then there's no subgroup you can form here. So there's no intermediate field you can form. So you cannot find all the roots in the quintic equation. Okay. Yeah, so this is the connection there. Okay. Because all the intermediate field extension must correspond to the normal subgroup of the Galois group. But if your Galois group happens to be A5, okay, A5 doesn't have subgroup, so there is no normal subgroup you can find. So there's no intermediate subfield you can find. Okay, you cannot find all the roots. Yeah. But why this theorem works, we have to leave it to later. Okay or no? Yeah. So the story you should get is, I have a group that don't have a subgroup. Then there's no intermediate field extension I can find. So what does it mean by field extension? I need to adjoin root, right? So there's no root I can adjoin. I cannot find the root of the okay. Okay. Yeah. Okay. Yeah. So this is about Galois theory. So we use group theory to learn about the roots of the polynomials. Okay. Yeah. Okay. Yeah. Okay. So what time is it? 4:03. Maybe it's a good time to a break here. Yeah. So do you have any follow-up question? Yeah. Follow-up question? If not, maybe we take a break until 4:13, 4:13, and then we'll resume.
我发现一些问题。因为在这个 square root 减去啦，它不会有这个东西。
什么？
就是这个不存在这里。
什么不存在？
这个，因为
不存在哪里？
不存在这个 square root 减去。
你这个是 ring adjoin 这个东西嘛？这里面的东西就是 a 加 b 乘它嘛，对吗？
有点是我离走错，
你要说的是它不管什么，你这个意思说这个里面没有它，没有。
对，然后这个里面的东西它其实不是那种 polynomial，然后把这个 root 减去 sub 进去吧。
不然这样子讲呢，这东西是 isomorphic to 的吧？是不是这样？对。 对，你是说扫进去的意思是说，没有啊，这个东西是
对，
这个东
它在里面，
西是这样，
它在里面，它在里面，因为
对，这个东西是这样，
对，一再乘以那个，然后加上零。
嗯
OK，好，
嗯，没有，你要说的是来这边没有一个东西是 behave like s square 加起，这边
对对，我我刚以为这个不在里面，所以我来直接拿这一个来做，但是我发现到这个做不出。我拿这个，是做不出的。
你要是这个不在啊，这个里
对对
边为什么是它的加一不在？
对，
啊，
对呢，
也
然后有4个上，它几个上过其实4个不是
三加上他自己是这个
啊
，OK，
，OK，然后00跟11不算，
这样00跟11，
因为11做了2次，它就回去00了，不是？
想一下，
然后有点错，
哦，好像你对，好像你对，啊，你对，对，我们还有一个 actually，
现在是有5个啊，
没有，就是还有一个，OK OK，对，你对了，非常好，你对啊，这边还有一个，所以其实这个是谁诶？这个好像是 correspond to
嗯，
Q adjoin，让我想一下，我要 check 一下这个图，我想一下，yeah，对，还有一个 subgroup，对，
所以我是有5个上部啊，
然后这一个会 correspond to Q adjoin 6，想一下。现在我有点想不通是 square root 6怎么会 adjoin 什么东西会掉出 square root 2？应该是对的，还有一个对，这个好像是 square root 6，
因为如果你再把它想成是 product 的话，
什么是 product？
我不懂，我现在头脑已经是全部东西
Yeah
接不通了，
Yeah，
然后
没有，是对啊，是对啊，是对啊，这个 part 是对啊，但是现在是问如果还有这个，呀，
现在是问
问现在是谁，
那个
对不对？对，所以是这个 root，好像 claim 是这个，claim 是这个，这个肯定是对的，这个反正我加什么都可以，但是问题是这个怎么加上去？我想一下，哦，我知道了，哦，我知道了，这个可能这个就是刚才那个加法就好，这个就 adjoin 刚才那个东西，就是 q adjoin 6，然后再 adjoin x，再切掉就刚才那个东西哦，那个 x
X40，然后
x 加14，加1，10减10 square 加1，减10 square 加1，这样就这样，因为反正这全部东西，这个应该不是它的 root 吧？放一下，有 root 就找到了。
6636嘛
360嘛，这个空间加1，这个应该没有这样大耶，
6630，
36乘，还没有，就36
吧哦，
这
36，
样不可能，
不
这样没有，
是不是它 root，
呀，
不是，
这样就是这个咯，这样就是，哎，我想一下，它应该要 degree 2哎，这样我可以把这个变小一点去，我可以找一个 internal square root 2 square root 6的东西，
所以那个还是
这样
maximum，
啊，
所以那个东西还是 maximum。
对啊，等一下啊。 哪一个是 maximum？
这个人还是 maximum，
不 maximum，它应该 reducible。看你们想找这个了啊？你们是找
我还没有做到这题。
x 减这个 square 一下好像。啊，这个 square 一下就好。我想一下啊，这个打到什么 x square？它只要用 degree 2的东西就可以做出来了。要想一下啊，要用什么 degree 2的东西把它做出来？square root 6拿出来 ，square root 6拿出来，6×2=12，4×3。如果我能够 adjoin square root 2上去也行了，好像。如果我有 square root 6跟 square root 2里面，我也可以做 square root 3，对不对？这样我可不可以直接？这样我可以直接切 square root 2减2就好。里面有没有这个东西呀？也可以这样切，我觉得都可以哦。其实是不是？我也可以切，我可以切这个x square 减3，应该都可以，因为这个里面应该没有 root 2躲在里边。呀，都可以，actually 都可以。
我干你，我干你。
没有，我想说就是，我们这边的 degree 的，这个是 degree 4的 extension，所以也是你看这边的 order 会被除嘛，所以这边也有一个被除的 structure 在里面，所以你看我这边切的是 degree 2的东西，这边切的是 degree 4的东西，明白？
刚
那个 degree，你看这个 degree 会也是2、4这样，这边也是2、4这样。呀，所以如果我要 make sense of 这个东西的话，我这边是2 ，OK，但是这边呢也要2咯，2×2才会是4嘛，不对？这边吗？呀，就是说我想说的就是这一个 extension 要除这整条的 extension，跟这个一样，跟这个一样，就是这个 order of 这个要除掉，所以这边也要2咯，要除的话，对，还有一个。
就不然呢，只是就是0033，那我碰来中上。
是这样啊，全部知识都是0033的，没有一个知识是整合的。
记不起来。
哦，
他的我觉得还好。
这点也是 OK。知识就是这样，它就是0033，你整合起来了，你就很难扩张。它都是散的，还可以继续升，这个知识还可以继续升。不然的话，你整合啊，你以为只有一粒东西，它不是一粒东西，它是散的，全部知识都是散的，只是看你能不能拎在一起吧。明天怎么？
我应该是拿着assignment考着你。
哦，OK 啊，明天哈，我看看明天呢。
看来看。
再看，下礼拜也可以，礼拜日啊，拜日。Hello，testing。Okay, testing. Okay, sorry if my class torture you a lot, but this is how should a maths class go. Okay, you have to undergo mind torture every lecture. Otherwise, you can't grow. Because this is the only strength of a mathematician. This is the only strength. Because you are not like AI, they can do coding. Or you are not like, who else? Like the mechanics, they have a skill, hand skill, right? Maybe they know how to use this apparatus, they know how to use this scissor cutting, right? But you don't know. The only thing you can do, what's your strength, is your mind. Okay, so if you're not going to train your brain, not going to train your train your mind, then you are wasted. You surely will forget all these calculations. Okay, you will surely forget all these calculations. But if you train your mind strength is good enough, then you can put other stuff in later. You can forget this, but you see, you have a box, you have a small box. Okay, filled with a lot of maths now. And then you train it, then your box become bigger. bigger and bigger. Let's say one day you don't want to do max already. You take all the max away, but you still have a box. Then you can put other stuff into it, right? Okay, so this is the idea of it. So you have to train. It is hard, but this is what a max degree can give. Okay or not? Okay. Yeah, I mean, yeah. Yeah. Okay.
Quoted by Seng.
Huh? Yeah. I seriously think this is the only advantage pure maths can give you if you're not going to do pure maths. Yeah. Yeah. But this skill is not random course can give you one, or random people can give you. Yeah. So you have to feel privileged and grateful that you are here. I don't think there's any Malaysia institution is doing this. Can do this. I said can do this. Oh yeah. So you need to be at least grateful. If you think this is not your thing, maybe you should find a better thing. Okay. If you think that you have no choice, then live with it. Yeah. A lot of things you just need to live with it. You cannot do much. So the thing is how to feel grateful from the things that you experience is very important. Okay or not? If you feel grateful, everything will become wonderful. If you don't feel grateful, if you even if I give you a good things, you think that is a bad thing. Do you want to kill me or not? Do you want to destroy me or not? Do you want to disturb me or not? Do you think like that? 被害妄想症. You will think like that. You will. You will. Please, okay. Okay. What's about this maximal ideal? Corollary. Okay, what's about this maximal ideal? So I like geometry. So let's link back to geometry again. Okay. So what are the maximal ideal in C adjoint X? Okay, what are maximal ideal here? So C is the field. So just now I proved that every ideal in polynomial ring over field is principal. Okay, and then how about maximal ideal? Maximal ideal are generated by the monic irreducible polynomial. Okay, so you go and build any monic irreducible polynomial. Any polynomial can, what is the polynomial that are irreducible in CX? So here you need to have a theorem in your mind, which is the fundamental theorem of algebra. What does the fundamental theorem of algebra says? N. Yeah. N degree polynomials has all roots in C. Okay, so meaning what? You can split up all the linear factor. Okay, so the only maximal ideal here are just the linear factor look like this. Because you can split every the high degree polynomial into linear product of linear factors, because you can find all the roots there. Okay, no. So this is the maximal ideal here. So this is in bijective correspondent with what? Can you guess or not? Can you pick one thing out of x minus alpha? There's only one thing you can do, right? What can you pick from this x minus alpha? What's the thing that can change in x minus alpha? Is the alpha. What is alpha? Alpha is a point in C. So this is in bijective correspondent with the points in C. Okay. Yeah. So I go one way, of course, the other way we need to prove. Okay, it's not too hard to see why. Okay. So there's a bijective correspondence between this. Maximal ideal in CX correspond to a point in a complex plane. Okay. You take a point in a complex plane, you can build a maximal ideal. Just take x minus alpha. Okay. And every maximal alpha, maximal ideal in CX is just x minus some point in C. Okay, you send that ideal to the point alpha. All right, so there's a bijective correspondence here. So study points on the C is just equivalent to study ideal, maximal ideal in CX. One is polynomial ring, one is complex plane. Okay. Okay. So next, we can generalize this. Okay. There's no there's no reason why we should stop at one variable. We can go to higher variable. Okay. We can go to maximal ideal in C adjoint n variable, for example. Okay. So what should this correspond to? What are the maximal ideal here? Maybe we talk about maximal ideal here, then we can talk about what's the bijective correspondence here. So what are the maximal ideal in a C adjoint n variable? You can check that these maximal ideal are the ideal generated by n factor, x1 minus a1, x2 minus a2, and until xn minus an. Okay, n of them. Okay, in this case here, you can have a bijective correspondent to points in Cn. Okay, points in Cn. So you correspond to an n-dimensional complex space. Okay, yeah. And send this ideal to the point A1 up to AN. And this is the famous theorem which we call the Hilbert's now Stellan-Stutz theorem. Okay, this is a German word. Now is zero, now space. Stellar, if you know interstellar, so it's like places, stellar. Stutz is a theorem. So if you read a German paper, you will see a lot of Stutz dot, Stutz dot, Stutz dot. It's like theorem dot dot, theorem dot dot, theorem what, theorem what. Okay. So it's a zero. Where do you find the zero? Okay, this is a very basic theorem you will prove once you go into algebraic geometry. Okay, but this is not satisfying actually. Okay, so the last thing we introduce is this. So we don't satisfy up to here. Remember that we introduced group. The last thing we introduce is quotient group. We introduce ring. The last thing we do is quotient ring. So quotient ring, quotient group actually are very hard concept. So if you get lost there, it's natural. But make sure you wake up again. Okay. So what we can do is we consider an ideal generated by R polynomial. Okay. We can again look at the maximal ideal in the quotient ring. Okay, quotient ring of C x1 up to Cn. Quotient by the ideal. This is what? This is correspond to the zeros correspond to the zeros of Fi up to Fr. Okay. Yeah, so you have a polynomial. You consider the zero. So for example, x squared equal to 0. What's this curve here? This is what curve is this? X squared equals 0. This is just a point, right? It's 0. Yeah, it's just a point. Correct. Yeah. What else? What kind of 0? For example, y minus x squared equals 0. What are the zeros here? This 0 is the graph, the parabolic graph. then if you consider in R2. Okay, so actually we have seen this example before actually. So let's go back to example we have did. So maximal ideal in the quotient ring. We have did one example. And we introduce quotient ring. Let's see. Yeah, where is it? Yeah, this guy here. This guy. Let me see. Is it this guy or this guy? Yeah, this guy here. So last time I asked you to identify the ideal of this quotient ring. Ct over t squared minus 1. Okay, and then we use correspondence theorem to say that only the polynomial that divide t squared minus 1 give you the ideal. I don't know, the concept representative. Yeah, so there are only 4. Using correspondence theorem, there's only 4 ideal inside this ring here. Okay, what are these 4? These are exactly 1 plus the ideal generated by t squared minus 1, and then t minus 1 plus t squared minus 1, t plus 1 times t squared minus 1, and t squared minus 1. So which one of them is maximal? Just now we said that maximal are the monic irreducible polynomial. But here, this is C, right? CT, CX, right? CT. So in CT here, what are the form of a maximal ideal? They are the linear factor. So linear factor here is what? T minus 1 and t plus 1. So there are only 2 maximal ideal here. So just how we said that there are bijective correspondence between maximal ideal and point in Cn, right? So there are 2 maximal ideal here correspond to 2 points, the 2 zeros of this polynomial. What are the 2 zeros of this polynomial? 1 and minus 1. Okay, so the t minus 1 and t plus 1 correspond to the 1 and minus 1 of this 0 of this polynomial. Okay, so studying the 0 of the polynomial is equivalent to study the maximal ideal of this quotient ring. Yeah, so this is the idea of algebraic geometry. So we study geometry, we study the algebra part of the geometry. The algebra part, we study the quotient ring, the ideal. Okay, what happened to the ideal? What's the relation between these two? Okay or not? Okay. 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 So maybe let's go a bit further a bit. Okay, let's do it. Yeah, so this is about maximal ideal. So you see that I have a ring. If I quotient out maximal ideal, I get a field. But I also introduced integral domain. Is there anything that I can quotient out by a? Is there anything that I can quotient a ring by so that I can get an integral domain? Okay. So this is what we call an prime ideal. Okay. So prime ideal is actually more general than maximal ideal. Okay. So what's the prime ideal? So an ideal is prime if AB is in I, then either A in I or B in I. Okay. So the proposition is an ideal I is prime if and only if R quotient I is an integral domain. So this is one way you can get integral domain. Z is an integral domain. Okay, maybe maybe we won't prove this. The proof is quite routine. Okay, what's the integral domain? Integral domain means for every AB equals to 0, either A is 0 or B equals 0.
right? So here I translate it into an ideal. For every AB in I, A in I or B in I. But you're quotient by I, right? So meaning either A is 0 or B is 0, right? Inside the quotient ring, I mean. Okay, yeah. So the corollary here is important because we're gonna link maximal and prime together. So let R be a ring. So the zero ideal of R is a prime ideal if and only if R is an integral domain. Okay. So this is kind of similar to what we have for field just now. Okay, if zero ideal is a maximal ideal, then if and only if R is a field. And B, a maximal ideal is always a prime ideal. Okay, maximal ideal is always a prime. Okay. It kind of makes sense because if you take a ring quotient marked by the maximal ideal, you always get a field. But a field is always an integral domain. Last time we proved that every field is an integral domain. Okay. Integral domain might not be field, but field is always an integral domain. Okay or not? Yeah, so I think up to here we have done with most of the ideals. Okay, and then the last thing I want to talk about is modules. And after module, then we can dismiss. Yeah, take a picture and then we dismiss. Last picture. Huh? Kanyan. I've been saying it for 2 hours already. Okay, sure. Okay, so last thing we will talk about is modules. Okay, modules is very important thing. Okay, if you're gonna do maths, you will keep seeing this. So what's a module? So the slogan for module is, a module is a vector space over ring. So it takes coefficient in ring, not field, right? Not just field, in ring, more general. Okay, so what is the definition for module? So let R be a ring. So an R module, okay, first of all, it is an abelian group with LOC. So we will write it as a vector addition, so it's a plus, and a scalar multiplication. Cos V to V, which is R comma V, sends to RV. Okay. That satisfy a field axiom. Okay. So this axiom should be common to you now. Okay. What kind of axiom you expect? Very good. I will comment about the 10 condition later. So first, you have 1V equals to V, and RSV, so R you take from the ring, X you take from the ring. If you compose this with V, you should get R compose X compose V. What's this? This is similar to the group action, right? Rx acting on V is equals to X acting on V and R acting on V. This is group action. 1 times V equals to V. Group action. Identity on V equals to V. This part actually is group action. Okay. What else? Always this property seems often. This is the distributivity. So R plus X times V equals to RV plus XV. And you can distribute your vector across your scalar also can. Okay. So meaning what? A module is a abelian group with scalar multiplication. This part is really the group action. Satisfy 1V equals to V, RSV equals to R times X times V. So you have a abelian group with a group action module. and distributivity law. And I don't need to list out the 10 property now. What's the 10 property you see in your vector space? They are really just the group property. Right. So let me show you. I've asked Jimbo to provide me your notes. Not sure you feel familiar or not. Right. For vector space, you have 10 property here. So what are these 10 properties? These are just group axiom with group action. And then plus distributivity. That's all. Then I can summarize the 10 vector space for you. 10 vector space axiom for you. Right.
This thing you have done is the real module.
Is a module over field. Yeah, module over field. Right. This is field, right? Let me see. Where is your scalar? It doesn't mention actually what scalar. Yeah, because your class is a real number. Yeah. Yeah, usually it's the scalar is the real number. Yeah. So when we talk about vector space, it's a module over field. Yeah. Okay. So how this module link back to ring? Okay. So let me link it back. So we have module. Definitely, we need to consider the sub-module. Okay, because if it's a set, we always can take subset. Okay. So what's the interesting subset here? Okay. A submodule of an R module V is what? Is a non-empty subset that is closed under addition and scalar multiplication. Okay. Usually, when we consider a sub of something, then we want to have a similar property that inherit from the original mathematical object. Okay. But for subring is a little bit different. Okay. Because Ting Yi sent a message to me, right? He asked whether a subset of a ring is a subring if and only if it is closed under the same LLC. Here, closed under LLC only. But subring is not. Subring has a very special element there, which is the multiplicative identity. Remember that when we treat ring homomorphism, right? We need to treat this multiplicative identity separately. I need to specify the multiplicative identity sends to multiplicative identity. It is not automatic. So to be a subring, you need to have the same multiplicative identity from the original. Okay. Yeah. Because we have one example last time. You can take an idempotent, multiply with your ring. This is a ring. Okay, this is a ring. This is a subset of your original ring. But the multiplicative identity there is not 1. It is the idempotent E. So it is not the subring of the original ring. Okay. Yeah. Okay, so this is submodule. So what about this submodule here? So proposition. So the submodules of the R module. Okay, we look at the submodule of R. R itself can be a module. It's like real number itself is a vector space. Okay, are actually the ideals of the ring. Okay, so they are equivalent. Submodules of R is the ideal of R. Okay, then we can generate another module theory to talk about ideals. Okay. Yeah. And then these modules will link to a representation because all modules are just representation. Okay. So row presentation. Presentation. One example already in your lecture content. What have you seen? Let G be a group, right? So if you consider G module, okay, this is in bijective correspondent to the permutation representation, assignment 3. Okay. Yeah, so this is one kind of a representation. Okay, so modules we can consider over group, over algebra, over ring, over Lie algebra. Yeah, any structure, any mathematical structure you can consider. It's just a group action. So scalar multiplication becomes just a group action. Okay. So it's very crucial to learn this. Okay, you learn group action, you learn what is group. Right? Then these two constitute what you need to use in your daily life. Okay, all the operation you did in your daily life. Okay, so we abstract the operation now, so that you don't need to list down one by one the 10 property. So we group the 10 property properly into different objects, and then we can study the object more systematically. Okay or not? Yeah, I think that's all I want to convey. At least this is my view on the algebra. Hopefully, hopefully you can get a better idea what the mathematicians are doing, and what's the prospect after this, and you can decide what you want to do afterwards. Okay, yeah. Any question? I think it's the last time I ask you any question. Yeah. Any question or not? We still have a revision class, right? Okay, so make sure you try the problem, tutorial, question, textbook before you come. You read which part you don't understand, then we can go through together. Online, right? Online, Friday. Have we fixed the timing? 2 to 4, okay, 2 to 4, yeah. Online 2 to 4. Okay, I will send out the announcement again to remind you. And then I have to return your assignment before that. Okay, yeah, and then we can discuss assignment there also. Yeah. Give some final thoughts. Final thought. I will talk for 1 hour and 45 minutes already. And then next semester, kissing again. I think quite unlikely. Very unlikely. Yeah. Very unlikely. How about later Peter assignment and then we do? We will see. So, we will see. Okay. Yeah. Or anything you want to talk to me? Your last word to me? I think I said a lot of last word to you already. Let's see. Yeah. Any last word? No last word. Huh? Yeah. Photos. Okay, let's take a photo before we dismiss. And we have Jinsen here, right? Jinsen can help us take a photo. Or you want to join the photo? Yeah. Yeah, let's take a photo before we leave, so that I can remember you.
结束啦。再长大一点啊，这个我操，你比较高，你现在你比较高。
看吧，我也去了。
就你过来一点了，
真的。哦，前面也要，他想过来一点，那边顶高前面。
那边不好看，然后待会儿，然后拍照拍照。它跟门有关系嘛？跟门有关系。你猜，怎么来看这个？啊，没有吗？没有没有。有啊，还是你也不错的，也聊天小。安哥笑一下。给这个表情的，对，1、2、3，再来一张，1、2、3 ，OK， 可以拍一手了。好，我。
发去 group， 发去 group 啊
？I don't know。
是你的 WeChat 它，然后
我
在哪来着？
我就是同学高哥的房间，
也是刚高哥的是。是啊是啊是啊是啊。说。
现在几分？
大几？现在几点啊
？5点。
5点。5点。
5点半。
5点半。5点半。
去先装东西先，这样早晚都。
5点半来得及吗？5点半来得及。哎，如果装东西先，我的摄像放下嘛。
没有，我
整理行李。
所以5点半，他讲。5点半，没问题。
5点半集合。
OK， 谢谢啊，谢谢。
5点半集合，你要在哪里集合
？B1 哦，你们就是每次在 B1。
对 ，B1 就是在 ground floor。ground
floor。OK，B1 ground floor。你记得提高这东西哦，记得说吗？介绍提高这东西。哎 ，Ryan， 护照出照去了。OK。OK， 你还没有发出第一版呢。肯定 happy， 肯定 happy， 一定 happy
啊，这没有 ending，
一定 happy， final， 一定 happy。
真的啊，你 happy 啊？
真的肯定 happy。
所以你在前面我只要准备关于 correspondent theorem 的东西就可以了。OK。
这样我要背啊，我要背theorem 咯。
为什么
不能很谢谢的，
没有，
也没有后面的句。
没有分的时候。就是assignment 全部有用到的东西，你能够不用
到位，那些用到的东西，